Hey there, welcome to Math 8, Unit 2, Lesson 6 on similarity. And so we're going to be exploring some similar figures today. And so as you talked in class today, you began with just a little question about equivalent expressions using what we know about operations and properties to write three expressions. And so you began with that thing right there, and you mixed it up a little bit. Perhaps you rewrote this as something like 10 times 2 plus 10 times 3, rewriting that distributed part there, minus, instead of 8 times 3, maybe you could do a 4 times 2, and then that value times 3. Just different ways you can play with order of operations and the properties to write that problem in a different way, but still end up with the same solution. It's kind of fun to play with some numbers. But today's lesson, again, the idea here is that these are similar things, right? They're a little different in how they're spread out, but you end up at the same place. So here we're looking at the similarity transformations. This is part one of this one here. It says that triangle EGH and triangle LME are similar. Okay, not congruent. Remember, congruent is something different. Congruent is going to mean that they are pretty much equal. Similar means they're pretty close. There's a pattern there for how they're connected, but there may be a different scale size. That's that scale factor kind of thing comes into play here when we're looking at something similar. It says find the sequence of translations, rotations, reflections, and dilations that show this. How do you get from here, this one, down to there? What's taking place there? And there's different ways to do this here. So it says they're similar. So if I was to take the smaller one, I can move it up to the larger one by first of all translating. I could translate point L all the way to point E, right? I could slide this one up to here to put it right there. Now by doing that, if I slide the whole triangle up, if I shift that whole triangle up, what I'm saying is that I'm taking this triangle here, here, and here, and I'm sliding the whole thing up to there. So when I do that, my triangle lands on top of the larger triangle at that position. So it would look like here is a triangle and here. And so my new triangle as its own little shape would be located there and there and there. So I'm putting my points L, and this becomes kind of my E prime, and then M. Maybe I could do L prime, M prime, E prime. So I'm translating from there to there. Now that gets me to that point, but to make this, to show that they might be similar and actually to kind of make it congruent a little bit, we could actually dilate this shape and turn it into that shape. So if we dilate this, we could have the center be E. We need to have our center dilation. Center is E. That's our center dilation. And then we have to look at what our scale factor is going to be. Well, this length is going to be right here. This is 4, right? So we have 4 right there. So we're translating there to there. And that's 4. And this one here is 2. So it depends on what I'm doing. If I'm translating the little one to the big one, okay, my scale factor would be, so to go from 2 to 4, would be 2. This is if I'm going from the little triangle to the big triangle. If I was going to go think about the big triangle going down to the small triangle size, then what would my scale factor be? It'd be the reciprocal, right? So it depends on which way you're thinking about it. So if I'm taking this as my real one, my first one, and I'm making that scale copy, then I'm doing a scale factor of 1/2. If I'm taking this one first and making that as my scaled figure, then I'm doing a scale factor of 2. Okay, so they're similar in that regard for how that works, and we can show the similarities and how that works pretty well. You can look at your tall length. You have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, and we expect this to be 1, 2, 3, because 6 times 1/2 would be 3, and so that scale copy idea works on that as well. Let's take a look at your next one, and this will go a little bit faster to these ones, okay? So your hexagon, you have this shape here and this shape here are similar. Find a sequence of translations, rotations, reflections, and dilations to show that. So we want to be able to show that this is similar. It's already given that it is similar, but how do we prove that? The way we're going to prove that is by getting this guy to land inside of that guy. So again, it's like taking a picture of it like so and making our copy. This is just a quick sketch. Taking this copy, if I want to get it down in this space over here, I'm going to have to do more than just the translate with a slide. I'm going to also need to do a reflection to get it flipped over. Okay, so what I would say is that you're probably going to take your first shape, right, and you do a reflection maybe over this point here. So you reflect it over line AF, so you end up with a reflected copy, right? So you have your reflected copy, and then you can translate point F, if you want to say, all the way to point I, and when you translate it there to there, then you end up with your shape like so. Okay, so your steps, your sequence of translation, rotation, reflections could start with a reflection over AF, reflecting there. And step 2, we translate E, or translate point F to point I. And then in order to make that copy thing happen, how do you make it work where you have a dilation? What's your dilation going to be? So we want to have a dilation. Our center, in our case here, we make our center be I. And our dilation, we're talking about our scale factor to go from one to the other. That's where you need to come back and do a little bit of measurement to say, well, how did I get there? How did I get from one to the other? And so when I take a look at, for example, this line here, let's look at the line F to E. So there's my line F to E. That's my distance right there. If I take this guy and drop it in place, hey, I got that actually right. There's one of those, and there's two of those, and there's three of those, right? So the distance here is 3, and my scale copy is 1. So again, if I'm going small to big, my scale factor would be 3. If I'm thinking about going big to small, my scale factor would be the reciprocal, and we would do 1/3. So make sure you are clear about what you're doing in terms of which one is being translated into which one. Okay, so that's the idea there. The next question, it's kind of fun. The circular grids are fun to play with a little bit, I think. Here we have a sequence transformation that takes triangle A to B and B to C. So we know our order. We're going from A to B, B to C. So we are definitely increasing in size. We're going to have a scale factor we know that's going to be greater than 1. We know that much. We can also tell that this thing is rotating some amount because it's spinning as it goes around. Don't know what that it's going to be, but it's definitely spinning. We could assume that this is going to be our center point and everything is rotating around that center point there. But we also can tell that it's kind of moving out, right? So seems to be some sort of translation happening as well to make it move away from the center point, which means I'm going to have a rotation, a translation, and ultimately I'm going to have a scale factor of some sort greater than 1. Okay, so those are my 3 things I'm probably looking for as I look at this triangle. When I take a look at initially, I can see that I have a triangle here, here, and here. And when I look at what's happening, if I take my point C there, if I rotate it, when I rotate this shape, I see that it doesn't line up on the next one, does it? As a result, that means there's going to be some sort of translation that has to happen to move it, looks like there, up a step, doesn't it? If I was to translate that point to the next one, I can go there, I'm going to translate it up again to go to the next one there, to that step there. And I translate it again, and I got to go up some more. So we're constantly translating this shape up a little bit more, or another unit or so up. To go from A to B, there's definitely a rotation and a translation and a scale factor as well. On this little chart here with a circular grid, if we took a line like this and we ran it through the middle, okay, we know from our math terms that this whole thing is 180 degrees to go from there to there, right? So it's 180. So all these little chunks have to be a portion of the 180 degrees. So think of it this way. I have 1, 2, and then I have 3, I have 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So I have 12 segments along that 180 degree measurement there. So if I took my 180 degrees and I divided that by 12, I'm going to end up with 15. I share this with you just to help you out a little bit. That means that every one of these spaces is 15 degrees. 15 degrees, 15 degrees. So if point A is being rotated from this line, I'm just going to draw a little bit larger, to this line, right? There's where A is at there. If I'm going to be rotation from there to there, I'm moving 1, 2, 3, 4, 5. Okay, I'm moving 5 segments. 5 segments is 5 times 15, and 5 times 15 is 75 degrees. So my rotation is a 70 degrees clockwise rotation. That gets me around the center, and I have to pat my center. Around the center. That gets me there. But when I rotate that, this point though is still going to be right there. Okay, so it's there. So my distance from here, center to there, is 1. To go from center to there is 2. So that translation part is part of my scale factor dilation. So it's not really a translation. The scale factor is going from 1 to 2, which means my scale factor looks like it's going to be a 2. Okay, and we could check that out with just some lengths of triangles as well. If I took a length at this back side, I have a length of here to here. And so if I put that over there on this triangle's edge there, we can see that if I go there, I got 1, and I got there, I got 2. So this goes from like a length of 1 to a length of 2. And so my scale factor is definitely going to be 2. So I'm going to rotate the shape 70 degrees clockwise around the center with a scale factor of 2 in order to create the next shape. And I'm going to do that again and again. And if you look at our point here, we're at 1, 2 away, and our next one, if we did 2 and we did a scale factor of 2, how far away should this be? 2 times 2 is 4. Check it out. We're at, from here, 1, 2, 3, 4. And so that's what's going to happen to move one shape to the next. Kind of cool. Fun way of looking at that there, but it's really fun to look at that circular grid and recognize that every space is 15 degrees. It's not like a 90, 60 thing. So everyone is 15 degrees. That's how you end up with that 70 degree rotation there. For 6.3, looking at their sketches that are similar to figure A, and it says sketch some that are similar and only use transformations listed below. So there's our shape. Just going to draw myself a little copy real quick, okay, just so I have it for the next pages. So I have a line, I'm going down, down, and down. Just a sketch. Okay, there's my cute sketch. I turn to the next page, and it says, do a translation and a reflection, label your sketch, figure B, and pause here so teacher can check your work. Okay, so my initial one looks like this, right? I'm going to make it a little bit smaller, okay, just so I can make it fit. So my initial picture looks something like that, right? Here's my picture. If I was to reflect it, I could reflect it over, you know, like the x-axis or the y-axis. Let's pretend I reflected over that line there. A reflection would look something like this, right? That's a reflection, check. And a translation means to slide it some way. So maybe I slide that whole thing over here. I end up with something that looks like that. I call this B. So I'm going from A to B with a reflection line and then a translation line. And that's your idea there, okay? Because does that work? Sure, that works there. So it's a translation and a reflection. Depends on how you want to look at it. I could have done the translation first. I could translate it over to here and draw that same thing right there, and then reflect over there. So you know, I end up in the same spot. For the next one, a reflection and dilation with a scale factor greater than 1. So let's say that I started off with a shape like this. Again, same shape. And we do a reflection over this line here. Okay. If I reflect it exactly the same, I end up with this. But because I'm doing a scale factor greater than 1, let's say it's times 2, I would not take that length there to there. I would double it from there to there, go to there to there. And this length here, from instead of here to here, maybe it goes out to here. And then that, instead of there to there, goes to there. And we end up with a reflection and a scale factor times 2. Okay, so again, this is just a quick sketch of how this works. You do this in class and make sure you get the idea. And then finally we have a rotation and a reflection. So if I started with something again like such, if I was to rotate this whole thing maybe that direction there, I would end up with it kind of snapping in place like so, right? That's the idea. I have that shape and I rotate it and I snap it down to that place there. So that's my rotation, and if I reflect it over that line, which I can, I'd end up with it sitting right there in that point there, point D. So some just ways to move things about: reflections, rotations, and translations. There's one more here, a dilation with a scale factor less than 1 and a translation. So if I had the initial shape again, If I do first a scale factor less than 1, that would mean I'm going to make a smaller version of that shape there. And if I translate it, I just move that down and out of the way, and I'm over there. Okay? Next one, your teacher's going to give you a set of 5 cards and your partner a different set of 5 cards. Using only the cards you were given, find at least one way to show that triangle ABC and DEF are similar and compare your methods. So we have some cards here, and the idea is to show that these guys are similar. As you work through that, you're going to notice that you can move this to there or that to there. You have your center dilation P. If you just simply copy this one over for now, again, you're working on this with your partners. If I take this one down here and kind of drop it in place here, it lands about here, here, and here. So if you layered those triangles, you can see that they're going to be located here, here, and here. And so we have some very common things in with these triangles, right? They both have right angles. They both have the same inside angle there. And then also these guys are technically going to be the same as well. So we know that these are similar triangles in that regard there. We can look and say that we have 1, 2, 3, 4 as my length. This guy is 4, 5, 6, 7, 8, 9, 10, 11, 12 is the length there for the whole thing. Tell me there's a scale factor from small to big of times 3. But if I was to go that way, we would say it is the reciprocal times a third, so depending on how you look at it. So you're going to work with your partner on that to figure that out. Again, because you have this center point P, we know that our lines are going to go through the vertices again and again and again. Let's see if I can do this one freehand, something like that. And so everything's going to line up, and that is how we translate and dilate that one there. So in summary, today's lesson, we can show that triangles are similar. Right? If one figure can be transformed, so two figures similar, if one can be transformed into the other by a sequence of translations, rotations, reflections, okay? And here's the deal, we only need to describe one to show that two figures are similar. So if we can get them to line up, we're going to be in great shape. So this is your example there. If I can get this shape to snap into place right there on top of that shape, then I can show that the smaller one is similar to the larger one. And so you can see we did a line of reflection and then a rotation, and we're in place there to show that those things are similar. Okay, so that's your lesson. So pause there, start working on your homework, and then press play when you're ready to check your solutions to see how you did. Okay, so tonight's homework. We have each diagram has a pair of figures, one larger than the other. For each pair, show that the two figures are similar by identifying a sequence of translations, rotation, reflections, dilations that takes the smaller one to the big one. So we're going smaller to larger. Okay, no problem there. Remember, to do this here, we need to know a couple things, right? We're going to need to figure out what our scale factor is going to be. So smaller to larger means I'm going to have a scale factor greater than 1. Because it's increasing in size. I also am going to want to pay attention to what's happening in terms of location. I need to know my center. What's my center point? Where am I translating this thing from or dilating it from? In this case here, we're going to say we have a center of dilation of 0.00. Okay, we're going to center it from there. We're going to translate A to point C. We're going to translate A to C is what we want to do first of all. We're going to slide it from there to there. And when I put that shape in place right there, I'm moving it there to there. That's where A, B, and C are at. Now I have it in place so I can see where it's at. What's happening to get from this size to that size? That's a 1 and this is a 2. We're going to be doing a scale factor of 2. So we would say dilate with center A, and our new one, center A, by scale factor of 2. So in terms of our steps, we translate A to C, and then we dilate with center A by scale factor of 2. So that's, in a sense, my steps there to translate from A to C, move to there, and then dilate that with a center of A by scale factor of 2. Okay, so that's my idea. So my center point initially was 0, 0. So we can erase that now. Not worried about it because once I translate it, my center point is A. But that's the idea. How do you put it on top and layer it and then make a new center point to prove that it is equal is the idea. Let's look at this next one here. We're going to translate here the little one to prove the little one similar to this one here. And we have our measurements again with the circular grid. Remember we said before that these are 15 degrees. So I'm going to go over from C to C. From this line to this line is moving it 1, 2, 3, 4. 4. We said they're 15 degrees. So that means it's moving 60 degrees and we're going this direction, so counterclockwise. So our first step would be to rotate counterclockwise 60 degrees with center being, in this case here, with center A. Okay? That's going to move this from here to about here. But when I'm here though, I got to now then figure out what my dilation is going to be. So initially I'm at 1, 2 away, and now I'm going to go to 4 away. So to do that, I would do a dilation with a scale factor of 2 with A as the center. Now I probably need to add a point here. I'm sorry about that. This is really point 3 to do it the way they want us to do that there. So step 2 would be to translate, I'm getting ahead of myself, sorry. Translate C to C double prime. So put that back in there. Sorry about that. What they're wanting you to do, just so you can see how this lines up, is step 1. What we're wanting to do is to do the rotation to there. Step 2, we're going to want to drop it in place, you know, here, or we can drop it in place there. So I went ahead and just went C to C, so there to there. And then we can go scale with a rotate. We can do the scale factor. We can make C as a center here if I did it this way. I was looking at my notes for how I did a different way. There are other ways of doing it, okay, so be careful. So we rotate it 60 degrees with a center of A. We translate it to C, and then we dilation of that with that being C to keep it in the same place. So that's one way of going about doing it. Are there other ways? There are, to get from there to there. So the idea is you got a rotation, and then you're going to translate it up so it snaps in place, and then you're going to go ahead and do your dilation there, right? So if you wanted to rotate it and then get D to that spot and then say D to D and then scale factor times 2, no problem. So they all work. It's up to you what do you see and what do you want to do there. Okay, number 2. Here we go. Here are 2 similar polygons. Measure the side lengths and angles of each polygon. What do you notice? So first of all, with our side lengths, we have a length of 3. We have a length of, let's call this one right here 1. We know those ones there. Something similar here, we have a length of 2, and we have a length here of 1, 2, 3, 4, 5, 6. That length, hard to say. I know it goes over 1, up 1, over 1, up 1. This one seems to go over 1, up 1 one time. There's like one of those thingies, and then here there's 2 of those thingies. So what we notice is that there definitely is a scale factor of 2 to go from there to there. Okay. The other thing you might notice if you took out a protractor is that these angle measurements here and here are equal, and these angle measurements here are equal, and those angle measurements here are also equal. So our angles are congruent, and that there is a scale factor of 2 to go from ABC to, or ABCD, sorry, to EFGH. There's a scale factor of 2. Each figure shows a pair of similar triangles, one contained in the other. For each pair, describe a point and a scale factor to use for a dilation, moving the larger triangle to smaller. So we're going larger to smaller, which means our scale factor is going to be less than 1, right? You use a measurement tool to find the scale factor. So you have to use a measurement tool, lucky us. So we're going to go from the big one to the small one, here to here. Okay, so what does our center dilation need to be? That's the key, first thing. So our center of dilation, where is it going to come together at? And this one is going to be B. Okay, so we know where everything is going to point to that point there. Now our scale factor, we want to go from there to there, so we have to use a measurement tool to get from there to there. So on the initial one here, I might measure that, and I can say, well, that's 4.5 centimeters. I might use centimeters. And over here, I might measure that and say, well, that's going to be a little bit more than 1. Hard to say. So I have 4.5. Let's just look what 4.5 gives you first of all. So if I did 4.5 on the initial, these are my notes here for now. I haven't worked it out this way. So I did 4.5 or 4.5, and I can see that then my new one is going to be going to, we measure here, we're at 1 and it's like 11, right? So 11 millimeters, right? This is like 45 millimeters, and I'm moving it down to maybe 11 millimeters. Like, that's really ugly. If I divide those by that, that's my scale factor, something like 11 millimeters over 45 millimeters. Just not a very pretty number to work with. If this one here was 44, let's make it 4.4. 4.4, right? Then I end up with 1 over 4, which makes a little bit more sense for my scale factor. Again, if you took a post note of some sort like that, okay, and we got a mark and a mark, okay, if that's my little bit there, how many of those do I have all together? I got a bit, and I got a bit, and I got a bit. All right, so we can see that this really is divided into fourths, and so to go from the whole down to there, I'm multiplying by a scale factor of 1/4. So your book might be a little clearer than mine. Again, this is a photocopy, so sometimes the proportion changes a little bit, or the scale factor changes just in the photocopying thing. Over here, our center dilation, we would say, would be A for how everything's moving around, okay? And if I take a look then at this here, using just the paper version, okay, the distance from here to here, if I was to do that again, I would go there to there, and I can go there to there, and it lines up. So this thing is really broken into, right, thirds. 1, 2, 3. So to go from the whole down to the bit is going to be a scale factor of 1 over 3. And that's, again, not using a measurement tool. I know, I realize that, but it's just not working out very nicely with this thing here. If I did the millimeters again and try to get that as precise as possible, I can see again that now I'm at 40, maybe 42 millimeters, right, for the whole thing. And I can divide that, that's my divisor, and then I put this guy here, and I end up with, let's see, maybe 14. Is that about 14 there? 14 millimeters? And so if I reduce that down, you might get somewhere close to that. Somewhere close. Exactly, not exactly, right? If I use my calculator, I do 14 divided by 42, and I end up with, well, that worked out nice actually, 0.33 forever, which is the same as that. So millimeters does seem to work for that one. Does it always work? It's hard to say, but that worked okay. So millimeters worked here if I went to 44. If you're off by a number, you end up with kind of a crazy fraction, so just be careful with that. That's okay. Hope that helps out your homework. Have a great day.